Propagation and indicators. So what is propagation, and what are the indicators to tell us what's going to be good about it and what isn't? There are ways you can find out about how good propagation is likely to be. Every month of RICOM, as long as I've been getting RICOM, which is since 1975, they've had the propagation predictions, and there have been good years and there have been bad years. It's not actually that good if you're a serious DXer, because it doesn't tend to cover the little islands out in the Pacific. And I can tell you from studying propagation predictions for the Commonwealth contest last weekend, which is only ex-British Empire or current Commonwealth countries, that one end of Australia will have a totally different prediction per band, time, long path, short path, and the rest of the far ends in New Zealand are totally different. And it's the same with what Christmas Island would be totally different to somewhere like Mayotte, or so it doesn't go into that level of detail, but we'll touch on other prediction things later. You've all, I suspect, looking around the room, got some concept of ionospheric propagation, and this is what gets our shortwave signals around the world, hopefully not just the locality. And there's something up there called the ionosphere, and signals get refracted. They don't get reflected, they get refracted, as with light going through a prism, that type of thing. Very good reasons for that. But the ionosphere in its refraction does get a fair percentage of the signal back again. So you can see just some examples there of a signal going up and coming back down, and you get quite a distance on a single hop. There are 4 distinct layers in the ionosphere, which we refer to, and it's, the D layer is the lower one, about 75 to 90 kilometers. The D layer is problematic in that most frequencies, indeed, if you want to get into physics terms, wavelength really has trouble getting through the D layer. So the D layer tends to absorb as opposed to refract. The E layer, again, it's quite low, but for VHF 6 meters, particularly 6 meters, a well ionized E layer will get your 6 meter signals quite a distance. Then you've got the F layers. Basically, we have the F1 and the F2 layer, which, oops, don't press that button, which, I'll throw myself now, which tend to combine at night and just give you the one F layer. So effectively 4 different heights of things are going on. And if you look at those on a global scale, now, scale's the wrong word there, because scale's totally wrong. The sun relative to the Earth of that size is a long way out there. So the rays coming from the sun, if you think of them, there's no point in pointing at that. If you think of the rays coming from the sun, they're parallel from a great distance out. So more than half the available ionosphere is getting illuminated in the course of the day, and as the Earth rotates. The bottom line is, because the ionosphere is well above ground, that even when the ground is in shadow at dawn or dusk, that the D and above layers do get ionized. So you can see the effect when we're in daylight. All the layers are ionized. Then as we get into darkness, the D and E layers disappear, and the F1 and F2 layers combined. Now, it depends, this is all down to solar activity, and we're right at pretty much at the peak of the current sunspot cycle. So things like the F layer will actually last right throughout the night, but in the minimum between sunspot cycles, that's not the case. So you can actually find the 20-meter band can be open until midnight without any problem. And it all comes down to, we have a different set of ionospheric conditions during the day and to what we have at night, and that is a major bearing on the bands that we can use. Now, if the ionized layer is weak, signals can go straight through it, but that's sort of frequency dependent. The higher frequencies or shorter wavelengths go through easier. So if you take a 14 megahertz signal and just send it straight up, you will find at times on the F1 or F2 layer will be strong enough for that to be reflected straight back, but a 15-meter signal will go straight through. So it tends to be the lower bands will be the first to get refracted as the ionospheric layer builds up in strength, and the higher frequencies are the last. So this is why the 10-meter band, until really this year, a little bit last year, but particularly this year, 10 meters has been good, because the F1 and F2 layers have been strong enough to sustain 10-meter ionospheric propagation. Indeed, 6 meters. When I was out in Burkina Faso in November, a lot of the 6-meter contacts that were being made with Europe were F-layer propagation and not sporadic E or anything like that. So that really only happens at the peak of the sunspot cycle. So just looking at those again, back to the distances, really to get your signal any distance, it's the F layer you want to get to. And on the low frequencies, like 160 meters, 80 meters, and 40 meters, during the day, the D layer is just so strong that the signals can't get through. So you don't get long distance propagation on the low frequency bands during the day. But at night, the D layer is the first to go. As soon as it gets dark, D layer is gone, and all of a sudden those bands become alive. In fact, as we tend towards sunset, the 40-meter band, as the D layer starts to weaken, the 40-meter band opens generally half an hour before sunset. So again, it's sort of frequency specific, and the E layer doesn't really stop anything getting through. It does play a part at times, although not that often. So the F layer is our main concern for the higher frequency bands during the day, and also for the lower frequency bands at night once they can get through the D layer. And just trying to get the concept of those rings around the Earth, the daylight aspect and the nighttime aspect, because that's all part of our understanding of it. So basically the F layer is what we're looking at, and if you have a transmitter on one side and a receiver on the other, you could have a distance of maybe 1,000 or more miles in that on a single hop, you get quite a distance, whereas on the HF bands, particularly on the high frequency bands, the ground wave is only sort of 50 miles, depending on your power antennas and the rest. But you need ionospheric propagation to get anywhere. There's also a downside in that in between those 2 points, you've got a skip zone, as it's known, where you can't hear the station. And the irony is, as you move further away, all of a sudden you start hearing it again. So that's one of the reasons why, particularly on the 2015 and 10 metre bands, G stations, if they're beyond the ground wave, tend not to hear them. Or if we do hear them, it's actually short skip, and there are other factors coming into play. You can then, having had one hop, you can be lucky and get a second hop. Now, if you come back to Earth over water, the reflection of the signal off water is better than the signal off land. And again, it depends on the land. If it's a mountainous region, you're not going to get a tremendous reflection. So you can have a second hop and come down another great distance away. I think normally for the United States, we're generally 2 or 3 skips to the East Coast. Again, that's a water path for us, and that helps. But if you're trying to get to Australia or something, you may be coming down on land a number of times. But that's okay. You lose a bit of signal each time you refract off the ionosphere, each time you come back to Earth. But you can have several hops. At the peak of the sunspot cycle, you can actually get to the point where the signal can go all the way around the world, particularly if you're Morse code. You can hear the echo of your own signal coming back. There are other things. The signal can be refracted, particularly if the E layer is intense, and there are things other than just solar radiation that ionize the E layer. But that's a different ball game. I'll not go into that now. But you can get something like your signal goes up, gets refracted a little bit, so actually hits the F layer much further along. So your signal skip can be noticeably more than it would normally be. You can get other things where the signal comes back down onto the E layer and goes back up. And again, you get a sort of unusual path. Most of the propagation prediction tools will actually show you contours where the signal comes down, will actually show the sort of presence of where the signal will be coming down. It can't take into account that sort of thing because that's a little bit fluky, although it does happen. You can extend that again, one F layer skip, then an E layer skip, and then F layer and the rest. But people have studied these things for years and years and years, and they do happen. A more common sort of surprise thing at times, particularly worldwide contests like CQ Worldwide, you can have general, or indeed when I was out in Burkina Faso, you would have hundreds of stations calling you, and they're all very weak. And then all of a sudden, you get this really strong United States station coming in, 2 or 3 S points stronger than anybody else. And again, this is what's known as chordal hop. The fact that you've gone up, been refracted, but stayed just below the F layer and been refracted again, your losses on that ground-to-ground path are a lot less than if you'd done a double hop and sort of come off the ground back up again. And you would get, just because of the sheer quantity of stations doing that, one would stand out, and it wasn't any better antennas or more power or anything. It was just on that particular instance, it was probably chordal hop, and that's not uncommon. It's hard on individual QSOs to try and determine, but in a case like that, where you do have a lot of stations calling, they certainly stand out. You can get a mixture of chordal hop and standard F2F stuff. So there's a lot of variety in what you hear. No 2 days will be the same. Even stations that are 50 miles apart in the United States might have totally different signals for a number of reasons. The various prediction tools, I like this VOAP Prop one. It looks up the solar data every day, although you have to tell it the sunspot number. And it's currently set for 20 meters. Sort of comes in those figures I think were either Saturday or Sunday, so that's very typical. I want to talk about the A and K indices in a minute. They're slightly on the high side, but this is giving a pretty good sort of view. Don't ever press that one. You got contours showing, in fact, waste of time trying to get anybody around me, but my first, should be coming down in this area. Just unfortunate to the west there isn't anybody there, but also I'm still a viable signal all the way out, so fairly good coverage, and that was pretty much what I was experiencing in the contest at the weekend. So there are tools that will translate that for you. Having said that, I'm more interested, and the reason why I display this, because I know about these things, I don't really need that to, just because it's saying that you can't work the west of Brazil, it doesn't mean that you can't. It's doing a prediction. It's not 100%. There's luck of the draw. This is the surprise, the charm of our hobby. What I really want to talk about here is grey line, which is this bit between dawn and dusk. Funny things happen if we're in the middle of grey line, that our signals can be ducted actually along the grey line. So I could have, around that time, my signal suddenly pop up in New Zealand, and indeed it did on Saturday, which is why I thought that would be a good example. So grey line gives a bit of an enhancement along that. The higher frequencies, it lasts a bit longer, 40 meters grey line, you could have an opening for 30 minutes, 45 minutes, less on 80 meters. On top band, 160 meters, the grey line enhancement might only last 2 or 3 minutes. You've got to be sitting waiting for it. There's another thing which people still refer to as grey line, I do as well. It's not correct, but it's sunrise and sunset enhancement, that when you're in grey line, that you have an enhancement effectively into darkness, which gives you anything up to 10 dB gain just as you transition through that. That's sunrise and sunset enhancement, but we tend to lump it all into the term grey line. Strictly speaking, it's not. But that's very good. I look for that most nights on top band. I will quite often be watching as grey line goes across New Zealand, across Australia, across Japan. I've never worked any of the countries, but someday I will, and it'll be because I'm doing that. And also, as the time of year changes, when we're in grey line, we're approaching the equinox now, where the grey line's practically north-south. But of course, that will change out into much more of an angle. So throughout the year, the points that are at the end of either grey line, or the sunset enhancement on one end and sunrise enhancement on the other, changes. So it's worth keeping an eye on that. I always display that or it's always on one of my screens.
Richard, can I ask a question if we go back one? If you're lucky enough to have a beam antenna, and just say you want to talk to or contact New Zealand, the Great Circle will tell you what direction to beam in.
Yep.
Would you, if you knew this and you were looking at this, would you beam due south?
I have Great Circle maps on the wall, and also with Logger 32, I have a map with Bangor in the centre. So yes, the beam headings. If you think about it, that Australia actually covers quite a range of directions.
Yeah.
I'll be talking about polar zone and things like that in a minute, but also long path, short path will also sort of come into that. But yes, I would use polar maps or great circle maps centred on Bangor, so my beam headings are true.
No, but in this, would you be going true to New Zealand in this example, because the path is actually running due south and the grey line following the grey line?
Yeah, this is what I'm talking about, the sunrise sunset enhancement into the dark area, as opposed to grey line following grey line. But that would be true, Keith, because that is a true representation of grey line, I believe. Yeah. The grey line is distorted on that map as much as everything else is, fitting it into a rectangle.
Yeah. Okay.
I don't know whether I have a great circle map. No, don't think I have. I actually reduced some slides. I did a similar talk in 2014. So you see this, the two screenshots here. Top one is 7th of March, where the sunspot number was 100, solar flux index was 150, very healthy, and the bottom one was Sunday, again 98 sunspots, solar flux index 148, very respectable. I show this every month in the magazine as an example. You can actually see, because there are 2 or 3 days between them, I think that sunspot group coincides with that sunspot group. The sun turns, to be awkward, the sun turns in the region of, at the equator, about once every 27 days. But further north and south, it rotates slower, to the point where I think about 75 degrees north, the sun is only rotating every, I can't remember, it's around 20 days or so. I'm doing a course in solar astrophysics at the moment. I should actually know that. But particularly with intense sunspot groups like that, they can come back round, but you do have to bear in mind that the equator is rotating faster than the rest of it is. And that's one of the reasons why we get these things, and we get the magnetic effects that happen within the sun and the solar dynamo and all the rest because of that. So the sunspot number is effectively a count of the sunspots. Many observatories counted, the sunspots have been counted for a long time. They use weighting factors to take early or sort of ancient sunspot numbers to make them comparable with the current ones. It's invariably a smooth sunspot number. You'll see SSN for smooth sunspot number. Not every source will give you exactly the same figure, but they're never that far out, and to all intents and purposes it doesn't matter. If you know sunspots, you're not going to have much in the way of HF propagation. So I'll actually just go back to read off the solar flux index. I'm around the 150 mark there. And the solar flux index is the amount of radio noise or flux emitted from the sun. It's scientifically measured, which is, it's not a big problem. You can build your own solar flux meter. Problem is you're only getting a reading when you're looking at the sun, so it doesn't work most of the 24 hours. The solar flux is very closely related to the amount of ionization and electron concentration in the F2 region, which is what we're interested in for propagation. So it's a very good indication of the X conditions, and the higher the better, but there's a sort of tipping point below 100, solar flux index of less than 100. conditions are pretty poor. Above 100, working Australia, New Zealand, under good conditions should be possible. So we always want above 100. The last solar cycle and the build up of this one, we had a long time with getting nowhere near the 100. I'm going to keep coming back to this because I'm going to pick out things. The A and K indices, I often mention them in the magazine in the month, and they are measures. I will come to those in a minute, what they're measuring, but basically the lower the number, the better. And between the 2 days, I'm just trying to work out my dates, the 7th and the 9th, so that was the Friday and the Sunday, so the contest, the Commonwealth contest was the Saturday and Sunday. So they're not good indicators because they're well above zero. And particularly on Sunday, the A index at 21, the K index at 5 was notionally bad news, but I'll come back to that. So there's a relationship, as you get for not having notes, the solar flux index and the sunspot number are related, and there is a formula which will cross-correlate between them. I did a little spreadsheet, me being me, just to compare the numbers that I had. I think the examples we had, the sunspot number of 100, I calculated a solar flux index of 145, whereas this says 150. And for the sunspot number of 98, it says 148, whereas I calculated 144. At the end of the day, it's not going to make a lot of difference, but it also highlights the fact that when you read these numbers online, you don't know quite how old they are. Whether they're just about to be updated, whether one has just been updated and not the other. But either is a good ballpark figure. You know that if you've got a sunspot number in excess of 50 or so, that the solar flux index is going to be reasonable. So I keep coming back to these. So now the A and K indexes, because they're a very key thing for us. The A index is it's really all about what's happening in our own magnetosphere and the rest, with what's been thrown at us by the sun. An A index of 0 to 7 is quiet. The Friday figures, A was actually on 7, but I think it was up to 14 or 15 on the Sunday, and that's unsettled. And then it goes on. You can see the figures. I don't think I've ever seen the A index above, I think, 190 or something. I think a few months ago that we did have one. I think it was when we had the brilliant auroras and everything. So you don't normally see the A index getting above the 50 mark. And just getting back to that was the A, and those two things was 7 on one, 21 on the other. So 21's not a good indicator. But the K index, the 3 and 5, looking at the K index, they're sort of quasi-logarithmic, which means they're like logarithmic. They're not quite logarithmic, but they're in the nature of. So 1 0 is inactive, 1 is showing activity, 2 is quiet, 3 is unsettled, 4 is active, and all of a sudden 5 is a minor storm, 6 is a major storm. So it's a sort of log scale, so you're never going to go over 9, and I don't think I've ever seen it above 7. Again, just looking at the figures, we were at a 5 there, so that was suggesting a minor geomagnetic storm. I'll elaborate on geomagnetic storms in a minute. Again, there's cross-correlation between them with the A index on the vertical scale and the K index. So the example of 21 equating to 5, so well, 21 is just about there. So it's approximately in that sort of figure. Again, there's a lag in the K index is that actually state there. The K index is computed every 3 hours, and the A index is computed from the 8 previous K index things. You've got to remember there's a time lag. So we can see from these two things that it's telling us that the HF bands, the daytime on the low bands is always poor. This is because of the D layer blocking the low frequency signals getting to the F layers. So that's a given. It's always going to be poor in daytime, and it's always going to be poor at night time on the 10 meter band, because it needs a reasonably strong F layer, and you're not going to have that in darkness. However, because of the geomagnetic stuff, you can see that it's marking poor on 30 meters, 20 meters, and fair on 17 and 15. So we can see there's an impact there, but we also have another factor, which is the BZ index, and that's interplanetary flux. And if that's negative, that's a bad indicator for us. So while the A and K were relatively low, solar flux was high, sunspot number was high, BZ was negative. The solar wind speed wasn't too bad. Here we've actually got the BZ as positive, and that's not such a problem for us, even though it's quite a big figure. The solar wind is quite high. So there was a bit of mitigation in that. I worked New Zealand and Australia several times on Sunday morning, so signals were still getting through. So it wasn't all bad. This is the magnetosphere. All this stuff coming out of a solar flare or coronal mass ejection is it's very strong magnetic flux. So it's impacting the Earth's magnetic field. It's actually compressing the sun side. The BZ index is actually the polarity of that flux. If it's actually going with our own magnetic flux, it's not so devastating as when it's countering it, in which case it has a lot more distortion of our own magnetosphere. With very high intensity coronal mass ejections, we're seeing things being ducted down into the polar areas, and this is the northern lights, the southern lights, the auroras, and that is problematic for us when that's happening. Again, just looking at, you can see the top thing is saying it's actually red, the auroral latitude of 66.5 degrees, slightly less in the lower one. The problem with that is you get this heavily ionized zone around the auroral zone, as it says. This is the 60-degree line, well, that's top of Scotland. We're, I think, about 54 degrees. But if you think about it, this is the equator on the edge here. So if you think of directions from us, anything sort of within sort of that arc means our signal has to go through the auroral zone, through very intense ionized stuff and the rest. You can get reflections of your signals. It was very noticeable both Saturday and Sunday with G stations, GM stations, auroral flutter. You get a very funny sort of warbling effect on the CW station or signal, and the sideband signals can be practically inaudible on account of that. But it also means if you're trying to get out into the Pacific, to all these areas, your signal's been seriously impacted by that. And I'm trying to remember, a couple of months ago there was a de-expedition, somewhere, I can't remember if it was Heard Island or Willis Island, something. It was new country for me, but the FT8 guys were struggling with that because the signal was so distorted because of the auroral or the polar effects on the signal that they weren't decoding. And I got them on a couple of bands on CW, and that's only as an experienced CW operator because it was heavily distorted. It was quite amazing to listen to. Just noting on there the units are ergs per centimetre squared per second. An erg is actually 1 joule times 10 to the minus 7, so that's a 10 millionth of a joule. So it's not a lot of energy until you think of the area that it's covering and the density of it. So that is an awful lot of energy around there, and certainly with ionization, stopping our signals getting through. So we are interested in the auroral latitude, and also that's a product of the BZ index. It's worse when the BZ index is negative. It's also worse when the solar wind is higher. But on the other hand, on the Sunday, the BZ was positive, although the solar wind was higher. So yeah, it was negative, but it didn't stop things because still a good bit of a good strong F layer. So again, it's picturing what's happening there. There's an awful lot happening with our magnetosphere. It's frightening actually to think just how much our magnetosphere is getting distorted, because that's what protects us from a lot of these things coming from the sun. And again, just there's a BX, BY, and BZ. They're just the terms that are used for the direction of these things. Again, we're just interested in whether BZ is positive or negative. So back to our core, this is what gets our signals around the world. When we have the high auroral events, or they get hit by a coronal mass ejection and have all this energy sort of inducted down towards the poles, we get geomagnetic storms where you get heavy distortion in the ionization of the F layer. So the F layer's ability to refract signals is totally destroyed, and you can get radio blackouts. That's one of the things. So this diagram is quite important. We rely on this, but say those particular geomagnetic events, which are the A and K indices, the BZ, the solar wind, the auroral zone, all go against that. So we can use those as indicators as to whether conditions are going to be good or bad. But there's variation in all these things. Radio blackouts, we've had, I think we've had 2 or 3 significant ones this year. We'll have more in the current solar cycle, but they're short term anyway. They're always transient things. But also there was the thing when I was out in Burkina Faso, because the sun is so intense, so near the equator, the D layer actually gets to such a strength in the middle of the day that 20 meters can't get through the D layer up to the F layer. So it's actually a blackout on 20 meters, and to a lesser extent 17 meters in the middle of the day. And you just have to move to another band because 20 in particular, but also 17 are unusable, despite because there's too much solar activity. Information about this, if you look at qrz.com, they've always got this little window on here. Have we got that focus now? So if you look at qrz.com, you'll get the latest figures on that. There are other sources. Solar ham, I could click on that and I should go to the internet, but I haven't connected to the Wi-Fi here, so I won't do that. But anything you want to know about solar information from the amateur radio point of view, you will find on that site. I'm going to list those at the end here, but I'll list all those in the next magazine, so you'll have a reference point. The RSTV has propagation news page. I had to hunt to find that. It's not something I refer to. Oh, it's very. I haven't actually read it. It is very generic. I wouldn't bother with that one. But it's nice if you want a general feel, which is what you get in RADCOM as well. Sort of non-specific. This is what you expect at this time of year, at this point of the sunspot cycle, as opposed to these are today's things. There's a very good document on there was a series of articles in RADCOM years and years and years ago. It must be pre-2014 when I first put together a talk similar to this, because I referenced this. The RSTV did then put the combined things online. Again, the link to that will be in the next magazine. I'll be on the screen in a minute. VOCAP is very good because you can, it uses the current solar figures, and you can look at it to actually get a specific path. This is looking at the path. Dates. I think I did that on Friday night, possibly with a view to the Commonwealth contest. I just want to know what the best times were for things. So given the current solar conditions, and you can tell it how much power you're using, and if you got a 5-element Yagi, monoband Yagi, you can put that information in. I have a cobweb, so it just assumes you got a dipole. So it will give you predictions for each of the bands, the likelihood of getting that, and suggesting that 10 o'clock in the morning that you might get Melbourne on 10 meters, which I didn't, either Saturday or Sunday. The contest ran from 10 Saturday morning to 10 Sunday morning. So that was useful. I printed those out for New Zealand, both ends of Australia, which is why they can stick categorically. They are totally different. Also Canada, being a major Commonwealth country, the Caribbean, there's lots of countries there, and Ghana, because I knew there'd be a station in Ghana. Well, Ghana, the path was open most of daylight hours in the high bands and low bands, potentially overnight. So that's very useful because it's very specific to the exact conditions that it reads online. It reads in the solar conditions itself. It'll also give you long path. So for somewhere like Australia, there are, I don't think I have long path on this, but I would have printed out long path and short path, because you've got different times where the best path is actually the other direction. It's slightly longer, but there's a better propagation path. And you get all that information from these tools. You know, you don't have to guess it. Doesn't mean that it's you're going to work along the paths that it predicts, but it increases the chances, and you know those are good times to be looking there. So I've got a list of the links there, but I'll put all those in the coming magazine. Solar cycles. We talk about solar cycle 25. How are we doing? It's one more slide after this. The first solar cycle is 1755 for solar cycle 1. Now, solar cycles have been measured for long before that. I assume some of you have heard of the Maunder years. It's been talk with the last solar cycle being very bad, and NASA's predictions was that this one was going to be even worse. and talk about extreme weather. The Maunder years, not hell froze over, but the Thames froze over, and for a period of 1645 to 17 something or other, when your man on the allegedly white Charger crossed the Boyne and the rest, that was the middle of the Maunder years. There were no sunspots, or very few and far between. There were no solar cycles as such, so for quite an extended period of 70 years or so, we had extremely cold weather or winters in the UK and the rest. And we don't really know why that happened, but solar cycles were being recorded before that. So the first one, solar cycle 1, is long after they started doing that. I don't know why they didn't go back further, given that they had the records. As a matter of interest, solar cycle 19, I was born in solar cycle 19. I was first licensed actually in solar cycle 20, and I was active in solar cycle 21. Solar cycle 22, I got married, and so I didn't actually operate in solar cycle 22. Solar cycle 23, I got back into it. 24, got back into it in an even bigger way, and 25, there's no stopping me now. The predictions from NASA towards the end of the last solar cycle was this was going to be an even weaker one. The next slide will actually look at the dips between the more recent ones, because they're quite revealing. But guys, I cited them several times in a magazine. Scott McIntosh and his mates did a scientific study, as opposed to what NASA do is they get all their experts to sit around a table in committee format, and they reach consensus. So there is no scientific backing to specific things in their predictions, whereas Scott McIntosh was a very detailed thing on how previous sunspot cycles had gone and the rest. NASA announced a few months ago that we'd reached the peak of the current solar cycle. And what on earth made them do that? Yes, the southern hemisphere has peaked, but the northern hemisphere hasn't. On a new solar cycle, the first sunspots start quite far north and quite far south. And throughout the solar cycle, they move towards the equator, but they don't always both meet at the same time. And we've had a number of solar cycles where there's been a very distinctive double peak. I think cycle 23 was a double peak, and my prediction, based on just what you can see by looking at sunspots on the sun, is sometime next year we should have a second peak. The other thing is the rise at the start of the sunspot cycle is much faster than the tail off. And while things were a little bit slow to start, when they got going, they got going, and things have been really good. And they'll be good for quite some time, because they'll tail off quite slowly. I haven't seen any formal predictions for the next solar cycle. And of course, Scott McIntosh is the guy I'm watching for. With the day his scientific paper gets published, I should get alerted on the thing. You all know. So just looking at this is a funny way of looking at things. Wikipedia is a great source of information. It's not peer reviewed or anything, but it's a great source. What they've done here is they're actually showing the solar cycle from the effectively the peak. So they're covering the minimum in the middle, and what we're looking at in the right hand column is the number of spotless days. Well, the last dip between the previous solar cycle and this one, we had 848 days without sunspots. You've got to go back to 1906, to the last time we had such a long period with no sunspots. But the previous, between cycles 23 and 24, was also an awful lot of spotless days. Well over the 800 mark compared to 200, 300 in previous cycles and the rest. So that shows you something of the variation between, NASA tend to assume that the next sunspot cycle is not going to be much different than the last one. And if it is much different, they're wrong. So we've got so many satellites and things monitoring all this information at the moment. Someday they might be able to predict a bit better, but I don't think anything that I've been doing solar astrophysics since last October, and I haven't learned any secrets that help unravel this, other than it's a mystery. All I will do, tell you, which you probably don't know, is that at the start of a new solar cycle, the magnetic fields on the sun reverses polarity. Now with an 11-year cycle, but if you think about it, it's only every 2 cycles that gets back to the way it had been. So long term, it's a 22-year cycle that you get the magnetic polarity being the same. But it starts off reversing the polarity, so all the lines, magnetic lines, are effectively from North Pole to the south, vertically crossing the equator. But most of this is going on through the plasma actually within the sun. So as I said, the sun is rotating faster in the middle than up as you tend towards the poles. So these magnetic lines actually get distorted. And over the years, they actually get wrapped time and time again around the sun. And this is why you get the eruptions of just due to irregularities. Nothing's perfectly symmetrical or sort of even in that all of a sudden you get breaks and magnetic line will come up above the surface. We get sunspots and the rest. They invariably, depending on the polarity, I think the flux always leaves on the pole side, but re-enters towards the equator. So you'll always see the 2 points where the line of flux has come out at a slight angle, so angle towards the equator. There are little things like that. I mean, that's been one of the fascinations of learning all that. But because of the complexity of that, you can't really predict it at all anymore. They say, oh, there's a cloud up there, it might rain, but then again, it might not. So we're a long way from being able to predict these things. But it's fascinating. Just the amateur radio thing, I must admit, the little course is quite fascinating too, apart from having to do assignments. So, any questions in that?
How were they measuring in the 17th and 1800s? All of this stuff just from observation? Or
well, as Galileo learned when he invented the telescope, don't look at the sun with a telescope. They just counted visually, which is why say, well, you can't see some of the smaller ones, which is why they use factors to just normalise the older figures and the rest of it. You could do things, you shouldn't look directly at the sun at the best of times anyway. Just a pinhole camera, a piece of cardboard with a pinhole projecting onto a piece of paper and counting spots. My 8-inch telescope, I've got a hydrogen, no I haven't, I've got a solar filter. I would like to have a hydrogen alpha filter, but for an 8-inch telescope it would be quite expensive. Anyway, you can look at the hydrogen alpha images online. They're very good because they really highlight the detail of all the little modules and everything on the surface of the sun. It's much better than looking at it yourself. But with the solar filter, it's fascinating to have the sun filling the whole field of view and seeing the sunspots. And there are classification scales for assessing sunspots and whether they've got penumbra or not and all that sort of thing. But the various sensors that they've got there, that the emissions from the sun in solar flares and CMEs, which are not the same thing, that different wavelengths. So there's actually more variation in the extreme ultraviolet range than there is on the visible light. So some of the space weather affects some of the stuff that actually gets through to the ground. We don't see much variation on a day-to-day basis because of filtering in the atmosphere and the rest. But for spacecraft up there, they take a hell of a beating. And even SOHO and the stereo the stereo satellites, one of which doesn't work anymore, they take a hell of a beating, and the sensors get overloaded every time there's a CME, but it's part of the design.
So check the sunspot number, and if it's too low, don't go out the shot.
Oh no, even during the minimum, there were still the expeditions, and it was they were harder to get.
Yeah.
And things like CQ worldwide, there hasn't been much variation in the amount of interest through the dip of the last super cycle and the rest of Commonwealth contest this weekend. I've been doing that for 2016, something like that. I've been the headquarters station for the last 7 years or something, and the activity, got more. I don't think I had any New Zealand stations last year, so that helped. But part of it is right place, right time.
Yeah.
And you've competition from better equipped stations than mine.
Have you a rig at the bedside?
Oh no. I do have breaks from the radio.
He has one in the toilet though.
There's one in the kitchen beside us.
There is.
Yeah.
The advanced thing is on the kitchen worktop, nearest point to the dish.
Richard, if you had a contact, say, from A to B, how do you know any sort of satisfaction, whether that it is double hop, single hop, or double reflection or refraction? How do you know which one it is, say, from here to, say, San Francisco? Not that it would matter, like, but
something. The example that I gave of Coral Hop, where you get one station just suddenly stands out against all others. A couple of S points louder than everybody else. There has to be something with that.
Yeah.
That.
So that would tend to be a refraction within another layer.
The signal's gone up, hit the F layer, gone across, and come down again. So it's done the same distance, but it hasn't come back to Earth. In that, so it hasn't had the losses that come through the reflecting off the ground, particularly if it's off land as opposed to water. And a lot of the time you don't, but certainly.
You can't say that's maybe what's happening, but you can certainly.
The auroral effects on Scottish and English stations at the weekend was very, very noticeable. And some of those, I was only getting them because of reflecting off the auroral curtain, because they were too far for ground wave, and I would have been in the skip zone. Indeed, there are specific stations that I know that I can't normally work on 10, 15 or 10 meters that I did work with the auroral sound on them.
Okay, listen, thank you very much, Richard. That was
Okay.
very educational.